Okay, so in this lesson we call it Strategy 3. We are going to continue using the techniques that we have in the first two strategies, but we're going to find that in these examples, when we make choices, such as choosing the denominator function as our u, it may not always work out, and we will have to choose the numerator function instead. This is why it's called the guess and check method. We're going to still go with our initial hunch, but if that doesn't work out, we will then choose the different function that's in the problem. As we become better at this through more practice, we develop pattern recognition, our guess and check should become more streamlined. So in this first example, typically we would choose the denominator as u, but we can see here that if u is x, we would get du as 1 dx, and this does not match. It does not address our natural log function at all, so we have to make a different choice for u. Our different choice is going to be natural log. We say, what if we let u be equal to the natural log of x, then the derivative of the natural log is 1 over x dx. And we should be able to see that this problem is the same as writing natural log of x times 1 over x dx, where the x is in the denominator. In doing so, this becomes our du, this is our u, and we can complete the substitution. We say, well, the antiderivative of u is 1/2 u squared plus c, and then we return u back to its original function. So we have 1/2 times the natural log of x squared plus c, and that would be our answer. So it goes against what our initial choice would have been, which was a denominator function, and we say now we see that it didn't work out. It's the guess and check method. Choose a different function in the problem. So we'll look at this again in example 2, and typically we would choose the denominator function, but we see the natural log is up in the numerator, and we just had success on example problem number 1 by choosing the natural log function from the numerator. So we're going to do that again. We're going to say, I'm going to have a hunch here. This is part of that pattern recognition that I was stating, that when we see the natural log, sometimes it's a good first choice. And when I do this, we want to recall the chain rule for derivatives of the natural log. So if I have d dx of the natural log with a function inside of it, remember that it is the derivative of that internal function over itself. So if we have let u equal the natural log of the cotangent of x, when we take this derivative du, it's going to be the derivative of cotangent, which is negative cosecant squared, over itself, which is cotangent x. And now we have to use some identities to help simplify this derivative. So I can write the cosecant as negative 1 over sine squared. And since cotangent is in the denominator, that means we can take the reciprocal of cotangent. We're using keep, change, flip. So negative 1 over sine squared times sine over cosine. And we see that one of the signs is going to cancel, so that du is equal to negative 1 over sine x times cos x dx. We see that we have this sine x cos x in the denominator and the dx. The only thing we're missing is a negative, so we would multiply inside and outside by a negative, because a negative times a negative is a positive, and our substitution step will give us negative antiderivative of u du, which gives us negative 1/2 u squared plus c, which is negative 1/2, and our u function was cotangent inside of the natural log plus c. So again, based on my experience from example 1, our guess and check, it started to streamline my choice for u, and I said I'm going to choose that natural log function as my u. So in this next example, what do you think we're going to choose for our u? If you said the natural log, that's a good choice. It's a good place to start. So we're going to let that be our u. And again, we're going to need to use that derivative of log rule. So if u is equal to ln of cosine of x, then du is going to be the derivative of cosine, which is negative sine of x, over the function that's in the log, dx. Well, we see that sine over cosine is tangent. We have a negative out in front. So du is negative tangent of x plus, negative tangent of x dx. We have everything we need to make this work. We put a negative on the inside and the outside. This is our u, this is our du. And once again, we have the negative antiderivative of u, which is negative 1/2 u squared plus c. And this time we'll be putting the natural log of cosine of x in place of u. And this whole thing is being squared. And there's our answer for number 3. I'm just going back. I noticed that I forgot to put my square on here because this did have a u squared. I should have had that written in there. Just going back, making a correction. And here's our last example. You see up in the subtitle, it says, choose the function in the exponent. That is going to be our u. We say, what if we let u be equal to x squared? Then du would be 2x dx. And we say, hey, look at that. We have the x and the dx. I just need a 2 in front of that x, and then a 1/2 to balance it. 1/2 times 2 is 1. That means we didn't change it. And then we can say that this is 1/2. Everything in the exponent becomes u, so it's e to the u, and the 2x dx becomes du. And what is the antiderivative of e to the u? It is itself e to the u. So we get 1/2 e to the u plus c. And then we have to do the back substitution. We have to put back the variable that this problem started as. And we have 1/2 e to the x squared plus c. And with all of these, you can always check your answer by using the derivative. Again, you need to use the chain rule derivative with u substitution integrals to get back to the original case.